The model of atom proposed by Rutherford assumes that the atom consisting of a central nucleus and revolving electron is stable, much like Sun-planet system. However, there are some fundamental differences between the two situations. While the planetary system is held by gravitational force, the nucleus electron system being charged objects interact by Coulomb's law of force. We know that an object which moves in a circle is being constantly accelerated, the acceleration being centripetal in nature. According to classical electromagnetic theory, an accelerating charged particle emits radiation in the form of electromagnetic waves. The energy of an accelerating electron should therefore continuously decrease. The electron would spiral inwards and eventually fall into the nucleus. So, such an atom cannot be stable. Further, according to classical electromagnetic theory, the frequency of the electromagnetic waves emitted by the revolving electrons is equal to the frequency of revolution. As the electrons spiral inwards, their angular velocities and their frequencies would change continuously, and so the frequency of light emitted must be continuous. So they would emit a continuous spectrum which is in contradiction to the line spectrum which is actually observed. Clearly, Rutherford model tells only a part of the story, implying that the classical ideas are not sufficient to explain the atomic structure. It was Niels Bohr who made a certain modifications in this model by adding the ideas of the newly developed quantum hypothesis. Bohr combined classical and early quantum concepts and gave his theory in the form of three postulates. Bohr's first postulate was that an electron in an atom could revolve in a certain stable orbits without the emission of radiant energy, which is contrary to the predictions of the electromagnetic theory. According to this postulate, each atom has a certain definite stable states in which it can exist, and each possible state has definite total energy. These are called stationary states of the atom. Bohr's second postulate defines these stable orbits. This postulate states that the electron revolves around the nucleus only in those orbits for which the electron momentum is some integral multiple of h divided by 2 pi. So the angular momentum of orbiting electron is quantized, that is L equals to nh divided by 2 pi. Let's try to answer why an electron don't radiate energy in stationary orbits. According to de Broglie's hypothesis, electron can move only in those orbits for which 2 pi r equals to n lambda. This equation is called as de Broglie's condition of stationary orbit. According to de Broglie, orbiting electron behaves as a wave and wavelength of the wave associated with the electron is h divided by p. Using de Broglie's condition of stationary waves, we obtained Bohr's condition of stationary orbit. De Broglie have also proved that the electron do not radiate energy in stationary orbit. While moving in a stationary orbit, electrons have particle as well as wave nature. As we know the concept of standing waves, energy gets trapped between the two nodes. Therefore, energy cannot flow. Hence, no energy transport. The wave associated with electron will form a standing wave, that is, energy will be localized. The wave will not propagate in the medium and there will be no loss of energy. Hence, these electrons will not radiate energy. Bohr's third postulate incorporated into atomic theory the early quantum concepts that had been developed by Planck and Einstein. It states that an electron might make a transition from one of its specified non-radiating orbits to another of lower energy. When it does so, a photon is emitted having energy equal to energy difference between the initial and final states. The frequency of the emitted photon is then given by nu.